When Einstein published General Relativity in 1915, the very first sentence shocked the world. Gravity is not a force. Physicists thought he had gone mad. But 3 years later, a total solar eclipse proved he was right. What's even crazier is this. Gravity is the weakest force in the universe. 39 orders of magnitude weaker than electromagnetism. What does that mean? Two people standing 1 meter apart attract each other with a force lighter than a single bacterium. If you wanted to build an instrument capable of detecting the gravitational pull caused by a person walking by, that instrument would need to stretch from Earth all the way to Saturn, over 10 billion kilometers long. And yet, in 2015, scientists really did detect gravitational waves. They were ripples in spacetime, created by two black holes colliding 1.3 billion light-years away. Even more unsettling is this. Right now, as you sit perfectly still, you are actually moving through spacetime, at 300,000 kilometers per second. Your brain just can't sense that speed. To understand how we got here, we have to go back to the year 1687. Newton published Philosophiae Naturalis Principia Mathematica, using a simple formula, to unify the motion of the heavens and the earth. An apple falling to the ground, and the moon orbiting the earth, followed the exact same law. That book changed human history. But Newton himself knew. His theory had a fatal flaw. How is gravity transmitted? The sun is 150 million kilometers away. How does it instantly pull on the earth? Newton said, I make no hypotheses. His theory provided the mathematics, but not the underlying mechanism. For more than 2 centuries, Newton's equations perfectly predicted planetary motion. Scientists even used them to discover Neptune. In 1846, astronomers noticed that Uranus's orbit was off. They calculated that an unseen planet must be influencing it. They pointed their telescopes to the predicted location, and Neptune was right there. But there was one exception. That baffled everyone, Mercury. Mercury's orbit shifts by an extra 43 arcseconds per century. That angle is so small, it's like seeing a fingernail from a kilometer away, yet it tormented astronomers for decades. Some proposed that another planet existed inside Mercury's orbit, but no matter how hard they searched, they found nothing. Until November 1915, Einstein used general relativity to calculate that missing 43 arcseconds, and the result matched perfectly. He later said that in that moment, his heart felt like it was going to burst. Nature was speaking to me, but what he was saying sounded insane. Gravity is not a force. It is spacetime itself that is curved. That sounds like nonsense, right? Spacetime around the Earth is like a stretched rubber sheet being bent. You think you're being pulled downward, but in reality, you are moving along the shortest path, through curved spacetime. On May 29, 1919, a total solar eclipse arrived. British astronomer Arthur Eddington traveled to Africa with his telescope to test a prediction. How much would the sun bend spacetime? Could it even bend light? Starlight passing near the sun should be deflected by curved spacetime, causing stars to appear shifted from their true positions. The results came in. The starlight was deflected by 1.61 arcseconds, almost exactly matching Einstein's predicted 1.75. The Times headline read, Newton overthrown. New theory of the universe. Einstein became the most famous scientist on Earth overnight, but that was only the beginning. If spacetime can curve, what happens under extreme mass? In 1916, German physicist Karl Schwarzschild, while serving in World War I, found a solution to Einstein's equations. He discovered black holes. An object with enough mass can curve spacetime to a critical point, forming an event horizon. Nothing, not even light, can escape. Schwarzschild calculated that the sun's Schwarzschild radius is 3 kilometers. If you could compress the sun into a sphere 6 kilometers across, it would become a black hole. Earth's Schwarzschild radius is only 9 millimeters. Imagine compressing the entire Earth into something the size of a glass marble. At the time, black holes were considered mere mathematical monsters, unlikely to exist in reality. But in 1964, Cygnus X-1 was discovered, the first confirmed black hole candidate. It was devouring a blue star, swallowing matter equivalent to 1,000 Earth masses every second. On April 10, 2019, the first image of a black hole was released. It was the black hole at the center of the galaxy M87, with a mass 6.5 billion times that of the Sun. Spacetime curvature also affects daily life. GPS. Why can your phone navigate you to within a few meters? Because engineers must correct for general relativity. GPS satellites orbit at an altitude of 20,000 kilometers, where spacetime is less curved than on Earth's surface. Time passes faster there, by 38 microseconds per day. If this error were not corrected, GPS would drift by 11 kilometers every single day. Your navigation app would send you to the wrong city. Einstein's theory is not an ivory tower abstraction. It works inside your phone every day. On September 14, 2015, humans detected the first gravitational wave signal, GW150914. Two black holes, one 29 times the mass of the Sun, the other 36, collided and merged 1.3 billion years ago, releasing energy equivalent to 3 solar masses converted instantly into pure energy. That energy spread outward as gravitational waves. On September 14, 2015, those waves reached Earth, stretching and squeezing, LIGO's 2 4-kilometer laser arms, by less than 1/10,000th the diameter of a proton. That precision is like measuring the distance from Earth to Alpha Centauri, with an error smaller than a human hair. The discovery proved that spacetime really can ripple like the surface of water. This was the final prediction of general relativity to be confirmed. Einstein predicted gravitational waves in 1916, but even he believed humans would never detect them. The signal was simply too weak. And yet, 99 years later, we succeeded. In 2017, the discoverers of gravitational waves were awarded the Nobel Prize in Physics. The citation read, "They opened a new window on the universe. Gravitational waves allow us to observe the cosmos in an entirely new way." On August 17, 2017, humans detected both gravitational waves and electromagnetic signals at the same time. Two neutron stars collided. The collision produced more gold, platinum, and other heavy elements than the Milky Way had created. In the previous 10 billion years, the gold ring on your finger, the platinum necklace you wear, were forged in the death dance of two neutron stars billions of years ago. They created the most precious matter in the universe. In a moment of destruction, now the question arises, if gravity is curved spacetime, where is the edge of the universe? What is spacetime itself? In 1917, Einstein proposed a bold idea. The universe is finite but unbounded. Like the surface of the Earth, you can keep walking forever and never reach an edge. Yet the area is finite. Earth's surface is two-dimensional, curved within three-dimensional space. The universe, however, is three-dimensional space, curved within something we cannot visualize. 4 dimensions. No one can truly imagine it. In 1998, astronomers observed distant supernovae and discovered something astonishing. The expansion of the universe is not slowing down, it's accelerating. This defied all intuition. Gravity should slow expansion, eventually stopping it, or pulling everything back together. How could it accelerate? The only explanation is an unknown energy driving space apart. Scientists call it dark energy. Dark energy makes up 68% of the universe's total energy. Dark matter accounts for 27%. Ordinary matter, everything we can see, is just 5%. We know nothing about 95% of the universe. Dark matter presents another mystery. In 1933, astronomer Fritz Zwicky discovered that galaxy clusters were moving too fast. Based on visible matter alone, they should have flown apart. There had to be invisible matter, providing extra gravity. This was dark matter. In 2006, scientists observed the Bullet cluster. After two galaxy clusters collided, visible matter clumped together, but gravitational lensing showed most of the mass elsewhere. Dark matter passed straight through the collision. This was the most direct evidence of its existence. Gravity also places a nearly insurmountable barrier on interstellar travel. The nearest star, Proxima Centauri, is 4.24 light-years away. At the speed of our fastest probes, it would take 70,000 years to reach. Even at 10% the speed of light, it would still take over 40 years. Accelerating just 1 gram of matter to half the speed of light requires as much energy as all of humanity generates in a year. For a crude spacecraft, the energy demand is astronomical. Time dilation makes interstellar travel even crueler. If you travel near the speed of light, your time slows down. You might reach Alpha Centauri in a few years, but decades or centuries would pass on Earth. Your family and friends would be gone. You would return to a world you no longer recognize. This is not science fiction. It is the iron law of general relativity. It happens every day. Inside particle accelerators, fast-moving particles live longer than stationary ones. What is the ultimate fate of the universe? If dark energy continues driving expansion, then hundreds of billions of years from now, all galaxies beyond our local group will be pushed beyond the observable universe. Astronomers of that era will look up at the sky and see only a few dozen galaxies. They will think, that's all there ever was. After trillions of years, all stars will burn out. The universe will enter the black hole era. Eventually, even black holes will evaporate via Hawking radiation. The universe will become a vast, empty darkness. This is the heat death of the universe. But that lies trillions of years in the future. Right now, the universe is in its most brilliant age. Stars are forming, planets are taking shape, galaxies are colliding, life is evolving. We are the universe's way of knowing itself. A small collection of atoms somehow understands gravity, spacetime, and black holes. With lives spanning mere decades, we comprehend billions of years of cosmic history. We detect gravitational waves. From billions of light years away, we photograph black holes, tens of millions of light years distant. Gravity shaped everything. Without gravity, there would be no stars, no planets, no you, no me. Gravity is both a prison, locking us into the solar system, and a cradle, giving birth to life. It is the weakest force in the universe, yet it governs the fate of everything. From Einstein's equation in 1915, to the detection of gravitational waves in 2015, a full century passed. Humanity spent 100 years, proving that spacetime is not a stage. It is an actor. It bends, it vibrates, it expands. The next time you jump, and fall back to the ground, remember, it's not the Earth pulling you down. You are moving along a geodesic, in curved spacetime. You are not fighting gravity. You are surfing the geometry of spacetime. This universe is more insane, more elegant, and more unbelievable than we ever imagined. And somehow, a group of ape descendants, standing on a small rock in space, managed to crack its code. That's it for today's video. See you next time.